In 2.18, we're told to find the probability current for the free particle and determine the direction that the probability flows. So as just a quick refresher, our wave function for our free particle, whoops, that's in red. Our wave function for our free particle is equal to psi k of x comma t is equal to a e to the I kx minus h bar k squared all over 2m multiplied by t. And then also the probability current formula, which was given to us in problem 1.14, states that the probability current for a wave function is equal to j of x comma t is equal to I h bar over 2m multiplied by psi multiplied by partial psi star with respect to x minus psi star partial psi with respect to x. So this is really just a matter of taking this and chugging and sort of plugging it into j and then just plugging and chugging away to actually get the correct answer. So let's write this out fully. Psi is going to equal a e to the I kx minus h bar k squared over 2m times t. Psi star is going to equal a e, and then we reverse the sign on the imaginary, so negative I kx minus h bar k squared over 2m times t. D psi with respect to dx, this is going to be, let's see, same a constant at the front, then the only x dependency is here, so we multiply it by ik, a ik times e to the I of kx minus h bar k squared over 2m times t. Similarly, partial psi with respect to x for the complex conjugate is going to equal negative a ik times e to the negative I times kx minus h bar k squared over 2m times t. Now if we plug this in, j of x comma t is going to equal I h bar over 2m, and then we have the psi term multiplied by partial psi. So we have psi multiplied by partial psi star with respect to x. We have two a's, so we have negative a squared, and then we have the imaginary times k, and then we have an exponential multiplied by its we have a complex exponential multiplied by its complex conjugate. These two just automatically cancel out to 1. Next, we have subtracted by, and then we have psi star, which is this, multiplied by partial psi with respect to x, which is this. So this term multiplied by this term, that's going to give us a squared times ik, and then the exponential will once again sort of cancel out. What we're left with is I h bar over m, and then negative a squared ik, where I combine these two to make negative 2a squared ik. The i's multiplied together make negative 1, so the negative cancels. This is going to leave us with h bar k over m times a squared. Now, let's see. Let me just double check that this is in fact correct. A squared h bar k over m. Yes, okay, that's correct. And this sort of implies that the probability flows in the same direction as the particle. Because remember, the direction of motion is sort of determined by the sign of k. So if k is positive, then it sort of represents particles moving in the positive x direction. If k is negative, it represents particles moving in the negative x direction. Correspondingly, if k is positive, then the probability current is positive, so that represents the probability wave function going to the right. And if k is negative, that corresponds to the probability function going to the left over time. So that is what we expect, and that does actually make sense.